For representing any higher order linear differential equation, the nth order linear differential equation, the nth order linear differential equation can be written as a naught dny dx to the power n plus a1 dn minus 1 dx to the power n minus 1 y plus a2 dn minus 2 dx to the power n minus 2 y. Similarly, plus a n minus 1 dy by dx plus a n y is equal to q, where q is a function of x. So let this be the first equation. So taking a naught dn dx to the power n common from, taking y common from all of these terms, so we would be getting a naught d to the power dn x to the power dx to the power n plus a1 dn minus 1 dx to the power n minus 1 plus a2 dn minus 2 dx to the power n minus 2. Similarly, an minus 1 ddx plus an, taking y common from this, y is equal to q. Let this be equation 2. Where a naught, a1, a2, similarly an are constants, constant coefficients, and q, as we know, is a function of x. We need not write the whole thing again and again. We can use a shortcut method to represent it. So for that, we would be knowing the concept of D operator. तो D operator क्या होता है? D operator होता है ddx. Any differential with respect to x is known as the D operator. So what would be d square? d2 dx square. What would be d cube? d3 dx cube. So similarly, dn would be dn dx to the power n. So substituting this in equation 2, therefore equation 2 becomes a naught d to the power n plus a1 d to the power n minus 1 plus a2 d to the power n minus 2 plus similarly an minus 1 d plus an y is equal to q. Since this is a function of d only, or we can write function of d y is equal to q. So here what is d? Remark, d is ddx. Always remember 1 by d would be integration of dx. This is an important formula that you need to remember. For a linear ordinary differential equation, the general solution or the complete solution has two parts, that is the CF or the complementary functions and the PI, that is the particular integral. So now we have to find out what is the working rule of finding out a general solution. So we have to find out the working rule of CF and PI separately. So the working rule of CF are working rule of CF or complementary function. So let's consider the differential equation of the form a naught dn plus a1 dn minus 1 plus a2 dn minus 2 as we have done previously. Similarly, an whole y is equal to q. So we have to find out ways of finding out the complementary function of this equations. So for a complementary function, first we have to find out what is its auxiliary equation. So for auxiliary equation, we have to put q is equal to 0 and put y is equal to 1. So what are we getting here on putting q is equal to 0 and y is equal to 1? And also put d is equal to small m in the equation 1. So what do we get? We get a nth order equation in terms of m. So we are getting a naught m to the power n plus a1 m to the power n minus 1 plus a2 m to the power n minus 2. Similarly, an is equal to 0. So this is our required auxiliary equation of the differential equation. It is also termed as AE. So what have we found out that we can represent our auxiliary equation in terms of m. So what is m exactly here? Here m is equal to m1, m2, m3, mn, where these are the n roots of the auxiliary equation. So the value of our complementary function, the value of the complementary function or CF depends on the nature of these roots of auxiliary equation. So depending on these roots of auxiliary equation, that is m1, m2, m3, mn, we can find out our value of the complementary function. So what is the cases? What are the cases? There is case 1 when all of these roots are real and are distinct. That is, they have to be real and they have to be distinct from each other. Then our complementary function is given as c1 e to the power m1x plus c2 e to the power m2x plus c3 e to the power m3x. Similarly, plus cn e to the power mnx. So similarly, what is the case 2? This was the case for real and distinct roots. So what if the roots are real and they are also equal? So in case of that, case 2, when roots are real and equal. In case of two equal roots, that is m1 equal to m2. So we have for m1 equal to m2, our CF would be C1 plus C2x e to the power m1x, m1 or m2, you can write it according to your wish, plus C3 e to the power m3x plus C4 e to the power m4x dot 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 Cn e to the power mnx. So this is case 2 for finding out the complementary function for two equal roots. So what if the number of roots, if there are three equal roots, that is m1 3 equal roots, m1 equal to m2 equal to m3. So what would happen then? Then our CF would be equal to C1 plus C2x plus C3x square e to the power m1x, m1, m2, m3 according to your wish again, C4 e to the power m4x, similarly Cn e to the power mnx. So we have now found out the cases for this would be in a similar manner. For example, there are four equal roots. It would be C1 plus C2x plus C3x square plus C4x cube e to the power m1x according to your wish, m1, m2, m3, m4. So similarly, we can find out a complementary function when the roots are real and equal. So what would happen if the roots are imaginary? We have in the first two cases we have found out for our case for the complementary function when the roots of the auxiliary equations are real. For case 3, that is when roots are imaginary. In pairs, they must always be imaginary in pairs. That is m is equal to alpha plus minus I beta. So when we are getting an imaginary root, our CF would be e to the power alpha x C1 cos beta x plus C2 sin beta x. This is our complementary function for when the roots are imaginary in pair, e to the power alpha x C1 cos beta x plus C2 sin beta x. Now we have a case also for when the roots are irrational. So case 4, when the roots are irrational. So for irrational roots, we can give as m is equal to alpha plus minus root of beta. So our complementary function in such a case would be given as C1 e to the power alpha plus root beta x plus C2 e to the power alpha minus root beta x. This would be our complementary function when our roots are irrational and in the form m is equal to alpha plus minus root over beta.